Hopefully you enjoyed lesson 26, the last problem, lesson 26. Because if you did, you're going to love this one even more. And if you didn't like it, you're going to dislike this one even more. Why dislike when you can like? Gravity on inclined planes. So now we're going to be we determine the acceleration of boxes and things going down a slope or up a slope, taking into account the friction. The one example of this lesson is determine the acceleration of a 15 kilogram box down a 30-degree slope, and the coefficient of friction is 0.15. Here's a sketch. 30 degrees. Here's the box. We might as well just make it a sketch/free body diagram. Let's draw our forces. Easiest one is always gravity. What opposes gravity? The normal force. Now, does it oppose gravity in a specific case? Not quite. Not quite, because remember, the normal force is always parallel to the surface. So the normal force in this case is not facing directly up, equal and opposite to the force of gravity, is pointing in this direction here, Fn. Right? What other forces? It's going down the slope. So the other force, then, there must be a force of friction going up the slope. Now, that's really the free body diagram, but it seems incomplete, because if that's the case, then what force is making it go down the slope? Well, that is obviously, its gravity is making it go down the slope, but it's a component of gravity. We're back to the idea of components. So it's not all of gravity, it's some of gravity. As a matter of fact, it's not much of gravity because it's only 30 degrees. And think about this. If it was really steep, if it was like it was 85 degrees, then almost all of gravity is going to make it accelerate down the slope. The less steep it gets, the less the components of gravity pushing down the hill is being used. So if you go to a really shallow slope, then because of the friction, there might not even be enough components of gravity to make it accelerate down the slope. Okay, so what's making it go down the slope is a component of gravity. So what we're going to do in these problems is we're going to separate gravity into components, which seems kind of weird because gravity is just straight down, is it not? Well, yes and no. Here's how we're going to separate gravity into components. We are going to separate it into this one here and this one here. This is a 90-degree angle. We are going to call, so the red one is FG. We're going to call, actually we'll color coordinate these. The green one, we're going to call F upside down T, which of course you know is not an upside down T. It's a perpendicular symbol. It's F perpendicular. And then the purple one, we're going to call that one F. If that one's perpendicular to the slope, then this one is parallel. So that's FG parallel, not FG11 or FG11. That is FG parallel. That is the force of gravity that's parallel to the slope, and that is the one that's making it go down the slope. The force of gravity that's parallel to the slope is the force that's making it go down the slope. That is very important. Because now if you look at that free body diagram, which looks a little convoluted, but let's just separate it into X and Y components. So not X and Y components, but components going in one dimension. So what components are going in the dimension that is parallel to the slope? This one and this one. And so you can write a net force statement with those. The net force up and down the slope is the force of friction plus the force of gravity parallel. Which forces are going perpendicular to the slope? And that would be Fn and Fg perpendicular. Okay, so hopefully we've got all that straight in our head. I'm just going to uncircle these so it just looks a little less convoluted. And from there, we can set about finding out what the acceleration is. What are we going to need for that? Well, we know the box is accelerating down the slope. Which forces, I'm going to circle them again. Which forces are going up and down the slope? That one. So we can write a net force statement. So we can say the net force up and down the slope in the direction it's accelerating equals the force of friction plus the force of gravity parallel. All right, and that's going to allow us to find the acceleration, because then of course we can say the net force equals ma, because it's accelerating down the slope, so parallel to the surface equals ff plus fg. This is, once again, you can do this in 2 steps, this part here, or 1 step, but we're not even close to getting there because we don't have anything useful yet. We have the mass. Do we have the force of friction? No, we don't, because we have the coefficient of friction, but not the force of friction. Do we have Fg parallel? No, we don't. So we need to go about and find out all that stuff before we can put it into this final formula down here. All right, well, let's start with some basics. Let's start with the force of friction. Let's actually just talk about, let's separate this into components first. We already said that the force of gravity going down has an x component and a y component. Not really x and y, but it has a parallel component and it has a perpendicular component, and this component here is Fg. Can we calculate any of those? Yes, we can. Fg is mg. M is 15 kilograms. G, 9.81. Multiply those together, and we're going to get 147.15 newtons. 147.15 newtons is the force of gravity. All right, so to find out the force of gravity parallel and the force of gravity perpendicular, we're going to need something else. We have a right angle triangle. We have one side. Let's just do this separately over here. Right angle triangle. We know the length of this side is 147.15. We need something else. We need either the length of one of the other sides, or we need an angle, one of the other angles. And we have one. You just probably don't know it yet. And that is this angle. This angle in here is 30 degrees. Well, this one's 30 degrees here. What a coincidence. Well, of course it's not a coincidence. Whatever angle is here will automatically be the same as this one. And I'm just going to do a little aside down here just to prove that to you from a geometry point of view here. Let's draw it. Actually, let's draw it really big. Really big. Wow. 30 degrees. Okay, I'm going to prove, so let's say that this right here is the force of gravity. That's the force of gravity, and the force of gravity goes straight down, so it creates a right angle right here. And I'm going to prove to you that here is the normal, here's the triangle that we have within the triangle. There's your force of gravity parallel. There's your force of gravity perpendicular. There's your 90-degree angle. Now let's fill in some angles there. If this one is 30, this one is 90, what's this angle in here? It must be 60. What about this angle in here? How many degrees is that? Well, this line, this blue line right here, which is now going to become purple, is perpendicular to the surface. So obviously this is a 90-degree angle. If this is 90 degrees and that's 60 degrees, and together they make 180 degrees, then this one in here must be 30 degrees. Okay, so there's geometric proof that the angle here is always going to be the same as the angle here. All right, let's go back. Oh, we can erase, yeah, we can erase that. Need it anymore? Well, you can go back and watch that if you need to be convinced more. And now 30 degrees. Now we can solve for our FG perpendicular and our FG parallel using trigonometry, using sine and cosine. So the sine of 30 equals FG. Which one is going to be? Opposite parallel over. Oh, FG parallel over 147.15. And just to move this problem along, we're just going to hurry it up a little here. FG parallel turns out to be 73.575 newtons. FG perpendicular, you find that using cosine. We'll go right to the answer there. FG perpendicular turns out to be 127.436. Okay, now do we need FG parallel and perpendicular? Well, we definitely need the parallel because the parallel is going to go right in here. Right, we can stick that in right now if you want. The FG parallel, 73.575. Now I'm going to put a negative there. Why am I putting a negative? Because that's the force of the gravity right here, pushing it down the slope. And I'm just going to make it negative because I know that the force of friction is pushing it up the slope, so we'll make that one positive. It doesn't make a difference. You can choose to make either one positive as long as the other one is the opposite sign. Okay, now I need FF, the force of friction. How do I get the force of friction? Well, I have to go back to my force of friction formula, which is mu times Fn. Mu is given to me. Is Fn given to me? And the answer is, well, now it is. Now it is because I've already calculated that. Right? And we know that FG perpendicular, look at our diagram over here, must be equal and opposite to Fn. Right? Equal and opposite because the object is not accelerating in this direction here. It's not accelerating perpendicular to the surface of the object. So therefore, Fn is going to be 127.463. We multiply those together and we get there an answer of 19.115. That is my force of friction. And now I know I can put that in here. What was the mass? 15. Was it 15? Yep, 15. A. And now I can put my force of friction in, 19.115. I'm going to make it positive because it has to be opposite. Opposite. And this is good because I can see that I'm going to get a negative answer, which I want because I designated it as down slope as being negative. So add those two numbers together, divide by 15, and you end up getting 3.6 meters per second, which is a pretty reasonable answer. Obviously, if you got greater than 9.81, then something is a miss because it can't be more than gravity. So 3.6 is a pretty reasonable answer, and there ends 14 glorious minutes of gravity on inclined planes. That's also the end of chapter 3. So get ready for chapter 4, which is all about gravity. Yay.